All right, we're gonna just add on to yesterday. Yesterday we were working with hydrolysis of salts, figuring out if we would expect them to produce an acidic, basic, or neutral solution. Today we're just going to take it one step farther and calculate the pH of a salt solution. But it's going to time what we did yesterday and be very similar to our weak acid and weak base calculations that we were doing last week. So in the next two questions, we're going to be focusing on the anions of the weak acid, and the anion is from the salt. So we know from yesterday when we have an anion of a weak acid, it's going to undergo hydrolysis with water. So it's going to react with water. Water is going to donate a proton to the anion to produce that hydroxide in solution, but it also reproduces its weak acid. Okay, the hydroxide amount is going to help us determine the actual pH, but we need that weak acid and its Ka to help us figure out what the Kb is. Because the issue is a lot of times we don't have the Kb value for the anion, but we can use its weak acid. So this next little part is just the background of how we are going to get to the equation we're going to use. It's basically looking at the reaction of a weak acid with water to produce hydronium and its conjugate. That conjugate is that anion of the weak acid, which undergoes hydrolysis. When it reacts with water, it produces hydroxide, which gives it its basic properties and then reproduces the weak acid. If you take the sum under Hess's law of those two reactions, you get the autoionization of water. Thinking back to equilibrium, if we combine those two reactions, their equilibrium constants, we would take the product of them. So by simplifying them down, we can see that the Ka of the first reaction and the Kb of the second reaction, their product would then end up equaling the Kw. So we can go between, like in this case, we can find the Kb of the anion from the Ka of the weak acid that you'll be provided. All right, so let's get into these calculations. All right, so our first one has to do with sodium acetate. So this would be our salt. And it's asking for the pH of the 0.25 molar sodium acetate at 25 degrees Celsius. And AC is just a simplification of acetate. So if we take our salt and just thinking back to yesterday, okay, when that dissolves into water, you have your acetate ion, and then you have your sodium ion. So we know that the acetate ion is that anion of a weak acid. Okay, our sodium ion is the cation from a strong base. Okay, so we're not going to see that react or interact with water. That would produce hydronium or hydroxide. That would affect the pH. So one little thing before we move on, though, is you should be able to use what we were doing yesterday to figure out about what the pH should be. So if we have a weak acid and a strong base, we know then that we would expect a basic salt solution. So I should see a pH that's going to be greater than 7. All right, so let's get into actually figuring out the calculation. So the step from yesterday that's going to get applied is that actual reaction of the anion with water. Sorry. And then so we know that water is going to be donating a proton to the acetate ion. So it's going to reform acetic acid and then produce hydroxide in the solution. So we can set up our ice table. Okay, so this is basically going to look just like a weak base calculation with one extra step. So our concentration was 0.25 molar. And then just going through what we did last week, we can simplify this down to our expressions at equilibrium. All right, so from here for the weak base calculations, we would use the Kb and sulfur hydroxide. Right now we don't have the Kb, we only have the Ka of the acetic acid. So we're going to take the Ka of acetic acid and then the Kb of your acetate ion. and that product would be equal to the Kw. So when we go to find the Kb, we're going to have the Kw divided by the Ka. So we'll have 1 times 10 to the negative 14th divided by the Ka of acetic acid that they gave us. Okay, and when you solve that, you get 5.6 times 10 to the negative 10. Okay, and then setting that up to against the expression that we have up above, we would have x times x over 0.25 minus x, which we will use our simplifying assumption, which we'll check at the end. So when you solve for x here, you should end up with 1.2 times 10 to the negative 5. And then this is where you guys have to be super careful, because remember that x value is not the hydronium, so you can't just plug it in to get your pH directly. You have to do a little bit of work, because that concentration is actually equal to the concentration of your hydroxide in solution. Just if you're filling the rest of your ice table, the acetate ion ends up rounding off to 0.25. If you do check your simplifying assumption, you get something like 0.005%, which is definitely less than 5%. So that one was okay to do. So then from here, it's just, again, this becomes the same as what we were doing last week. I personally find my hydronium ion concentration next, using my Kw, 1 times 10 to the negative 14th, divided by the hydroxide ion concentration. I just try to just use the value in my calculator the whole way through. So then I have my hydronium ion concentration, which ends up equaling 8.3 times 10 to the negative 10. And then my pH is going to be equal to my negative log of that, which I get a value of 9.08. All right, and that's what I would expect. I would expect it to be something above 7, so it gives me a good indication that I was probably right with my calculation. Okay, if you feel okay with this, I would pause it and try out the next one, the sodium nitrite, on your own, and then just double check your answers. If you still feel a little iffy, you can keep playing this on. All right, so we're going to look at sodium nitrite. So this again is our salts. We have NaNO2. Sorry, I didn't mean to make that look like a vector. You have your sodium ion concentration. You have your nitrite ion concentration. We know that this comes from a strong base, so it's not going to interact with water. This is our anion of a weak acid. And just like before, when you have that strong base weak acid combination, we would expect a basic salt solution. So we're expecting a pH greater than 7. So I am concerned with the nitrite ion and how it's going to react with water. So I have my nitrite ion. It's going to react with water. Okay, water is going to donate a proton to the nitrite. And then it forms hydroxide in solution, which will give it its basic properties. I'm going to go ahead and set up my ice table. So nitrite here is your 0.80 concentration. We're going to put in 0 for the other part here. We're going to fill in our changes in concentration based on the stoichiometry. We're going to, proceeding to the right, we're going to simplify our expressions to what they are at equilibrium. Okay, and then again, just like the one before, we need our Kb value. So Kb is going to be our Kw divided by the Ka of its conjugate, which is the nitric acid. And then we're going to go ahead and do 1 times 10 to the negative 14th over that Ka that they provided us. Okay, which ends up equaling 1.4 times 10 to the negative 11th. And then I can go ahead and set that equal to my expression. So x times x, or x squared, over the 0.80 minus x. We'll simplify that down, which will definitely be much less than our 5%. When you solve for x here, you should get 3.3 times 10 to the negative 6. And then again, really important, remember that is your hydroxide ion concentration. Again, that's why it's so important to write out these equations for yourself so you can keep track of that better. You can go ahead and fill in your chart if needed. This does end up rounding off your nitrite ion concentration to 0.80. And then also I didn't do the simplifying assumption there, but you end up getting 0.0004%, which we know is definitely much less than 5%, so that checks off. All right, and then just to finish up our calculation, if my hydroxide ion concentration is 3.3 times 10 to the negative 6, I'm going to calculate out my hydronium ion concentration, which you should be able to get as 3.0 times 10 to the negative 9. And then your final answer is taking the negative log of that. So you end up with a pH of 8.52, which is what we would expect, something greater than 7 there to represent that basic solution. Okay, so it's just really today just combining what we did yesterday in terms of writing out the equation, understanding is that anion in this case producing that hydroxide, or if I were to give you one where you had the salt of a weak base instead, being able to show how it produces hydronium, and then also just combining the weak base calculation. So nothing totally new today except for really, I guess, this expression here. Okay, but a lot of it is just combining different things together so you guys can handle this. All right, that is it.